Statistics at the University of South Carolina, upstate. So it's such an honor, Prof, to be doing this presentation with you in the audience. And to everyone else, feel much welcome. So I'm gonna take us through the WiDS DATATHON 2023 recap, whose theme was adapting to climate change by improving extreme weather forecasts. So this is one of the use cases whereby data science has come in handy to ensure that the efforts being put forth to improve these extreme weather events brought about by climate change and related issues has come in handy. So I'll just highlight my presentation, whatever we are gonna cover this evening for those who are in Kenya and the different time zones depending with where you are. So I'm gonna run through the overview of the DATATHON and then speak about the kind of data set we had, the data preparation processes we undertook, feature engineering strategies, and then I'll delve into the regression modeling aspect and the why the 1 to 5 were really necessary, why we really focused our efforts much on that. And then I'll take us through a number of diagnostic plots that I found to be key and worth noting. And finally, I will present the lessons we gained from here. So without much ado, I dive into the overview. So just giving a brief background of WiDS and the DATATHON. So WiDS is Women in Data Science, an initiative that was founded by women at the Stanford University, whose main objectives are to inspire and support women. Thirdly is to educate everyone, regardless of gender, on matters data science, AI, and even tech. So previously, these objectives have been achieved through organizing conferences yearly, annual conferences. But for the last 2 years, they took this a notch higher and introduced datathons where participants from all over the world come together and tackle a real problem to impact the society, but in the same process also get to learn skills related to data science, AI, machine learning, and generally just technology. So being an annual event, so the datathon for this year was rolled out in January 6th, where participants were to collaborate in teams of 4 with a 50-50 gender parity. Yeah, but people could also work on each as individuals, but we highly encourage people to work in teams to build that teamwork, collaboration, and get to learn from each other, as besides also appreciating the diversity of the different teammates. So what kind of data were we dealing with? The data was a weather and climate information data set, where we had weather and climate related attributes and a target which was a temperature over a 2-week period. In this case, we were looking at 514 unique locations in the United States. So we had 2 sets of data. We had a train set and a test set. The train set had 375,734 observations with the 246 features, if you like, variables. So among these features, 245 were predictors, and we had 1 target feature. The test data had 31,354 observations with 245 variables. You will note that this is less 1 variable in comparison to the train set. And the reason for this is because the test set didn't have the target variable, because that was our key goal, to predict the target variable, which was the arithmetic mean of the max and minimum observed temperatures over a 14 window period for each of those locations for a period of about 2 years, from 2014 August to 2016. How did we handle the data pre-processing phase? Number one, we undertook anomaly detection. So just a brief definition into what anomaly detection is. This is a machine learning technique that is used to identify variables or observations that seem to depict significant deviations from the norm or what is expected. So this was a very critical step for the kind of data we were dealing with, because we realized a number of observations or anomalies. So after we did this step, we dropped about 18,000 observations and remained with the 356,947. So what followed after this was missing value imputation. So this is the process. Imputation is the process whereby you we fill observations or values in observations that are missing with estimated values that are plausible for that specific observation and feature or column. So we had to do a number of feature transformation. This was encoding categorical features. We had the climate regions that were categorical features for the 514 locations. So we had to do label encoding for this to just ensure that it is in the right format for our model to be able to intelligently gain insights. So we also scaled our variables, that is the longitude and latitude, and used these two variables to come up with an improved new feature we were calling a location group, whereby each of the other features for all those days were grouped into one of the location groups, and dropped a number of features that were not really meaningful to the prediction task, such as the index variable. This was attributable to the fact that the index variable in itself, besides being a unique identifier, didn't have any meaningful value to the resultant data set and to the prediction task. So the next aspect was feature engineering, whereby we had to select features and transform the features we had by creating new features, doing polynomial transformations, among other aspects like means and deviations. We also did some feature interactions. So from a data set of 245 features, we ended up with 301 features after doing all this. Why was this necessary? This was also necessary because it helped us capture the nonlinear relationships in the datasets that could not be explained by the variables we had initially. So it was very necessary to come up with these new features that explain to a greater extent the underlying patterns and the relationships in the dataset, to give us that advantage in terms of ensuring we get very good estimates for our target variable. So we also undertook correlation, where this informed our choice of which variables to drop and which variables to keep. So we dropped variables that had a correlation in absolute of less than or equal to 20% with the target, and also dropped the features that were correlated among themselves. This was necessary because we wanted to remain with features that were minimal, but at the same time explained to a greater extent the underlying patterns in the data, and in return get very good estimates and achieve parsimony. So parsimony is the phenomenon whereby we have a simple model with fewer features but doing a great job in terms of a predictive capability. So the aspect now of the entire regression modeling, we began by creating baseline models. Here we made use of the PyCaret machine library. So PyCaret is an open source low-code machine learning library in Python that is used to automate machine learning workflows. So why was it necessary for us to use PyCaret? Number one is the efficiency. Since we hadn't interacted with this dataset before and couldn't tell from the word go which models would work best with this kind of dataset, it would have meant that we would build quite a number of models, each model one step at a time, to determine which models were better fits for the underlying dataset. So this came in handy because we were able to build several models at a go in less time, and from this we identified the top 3 models to move forward with. And this served as a benchmark to improvement of our predictive models. Something key to note here is that less effort was put in terms of tuning the hyperparameters of these models. We just worked with the default hyperparameters so as to have a baseline of where the starting point. So engage ourselves. Are we improving in terms of prediction scores and the capability of our models to give us a competitive edge in the competition? So we then moved to the next step of modeling outside PyCaret once we identified 3 best models. That was the CatBoost regression model, the light gradient boosting machine, and the extreme gradient boosting. So here now, our key goal of working outside PyCaret was to gain that full control and flexibility with regard to our modeling needs. So this would mean we would have more control on the number of hyperparameters to tune, on the approach of how to tune these hyperparameters and such like things. So our tuning approach was the Bayesian optimization technique, which is a machine learning optimization technique that involves building a probabilistic model of the objective function with the aim of choosing a set of hyperparameters to evaluate, with the goal of having very few evaluations that would give an optimal set of hyperparameters to work with. So this was a very advantageous approach to us, since it is known to be efficient because of how it does the optimization. And another thing, it is competitive in terms of giving very good model performance because it relies on previous knowledge, prior knowledge. This is an approach that is based on the Bayesian inference. Yeah. So we had also to implement the pseudo labeling approach, whereby after training our initial model, we made predictions on that best model and used those predictions, and in this case now calling them pseudo labels, use those predictions as if they were real target values in our initial data set. So what this meant is that we had our data set increased by the number of observation we had in the test, and then also made predictions using that iteratively to an extent whereby we achieved convergence, whereby no more training and retraining using this approach yielded better performance. Yeah. And then we also employed an ensemble modeling approach whereby we used the predictions from the three algorithms, CatBoost, LightGBM, and XGBoost, to get weighted a weighted prediction for as our final prediction for the parsimonious model. So why were all these approaches really necessary? You might be asking yourself, why did we bother so much? Was it worth the effort? And the answer is in the next slide. So here I give a step-by-step explanation on each of the approaches, the outcome we got, and the leaderboard score. Yeah, so once we implemented the anomaly detection technique, we gained from this in the sense that the instances that were eliminated had initially skewed the had initially introduced skewness and biasness, leading to sort of inaccurate estimates. So after elimination of these anomalous instances from our dataset, we managed to improve our initial score of 1.69 to 1.597, and this were leaderboard RMSE scores, that is the root mean squared error scores. So our feature interaction efforts led to the increase of our predictors from 245 to 301, giving us an RMSE of 0.87 and an improvement on the leaderboard, whereby we improved from 1.597 to 1.156. The efforts to drop features based on the correlation yielded a 0.948 leaderboard score, and then the final feature selection yielded our final score on the leaderboard as 0.831. Key point to note is that looking at these RMSE values, there was some improvement in terms of the RMSE value dropping, but the value started to increase slightly. However, this did not in any way disadvantage us in terms of the leaderboard score. So what am I trying to communicate here? We noted that finding that sweet spot in terms of the kind of features to use in our modeling and the number of features to drop was very key in terms of deciding how best our prediction capability would be. And here comes the importance of domain expertise. Looking at these first two approaches, one might, without looking at the leaderboard scores, one might say our efforts worked against us. That is the RMSEs deteriorated, but it didn't, because we introduced intelligent features into the model based on doing research widely, and we also consulted subject matter experts widely to inform which kind of variables should we drop, which kind of variables should we keep, and what kind of complex interaction should we employ. And that was a very key learning point for us. So I just take us through also a number of diagnostic plots and the key figures I thought worth sharing. So this was a grid of our initial model performances, our baseline models. So we shows the cut boost, XG boost, and the lat GBM. So this grid just shows the different model evaluation matrices, the mean absolute error, the mean squared error, the root mean squared error, the R squared, the root mean standard log error, and mean absolute percentage error, and the time in terms of the computation time in terms of seconds. You might be asking yourselves, why would we not move forward with the decision tree regressor, the third model, and opted for the light gradient boosting machine? So one of the key factors to consider when choosing a machine learning model is the computation requirements of this model. So it's very necessary and important for one to balance the predictive performance and the computation requirements. So looking at this, the decision tree regressor performed equally good as the first three. However, computationally, it was very expensive, considering these are average scores that are done for each of the falls at the cross validation. And that justifies why we had to move forward with the large GBM. So these figures here, figure 2 and figure 3, are diagnostic plots from our cut boost regressor, the initial baseline model. So looking at this residual plot, we see that the residuals are distributed around 0, an indication of a very good performance and fit of a model to the data. Then the prediction error plot also confirms that, because the baseline and identity line overlay on each other, indicating a good fit. This last figure here is the feature importance plot. My apologies, it looks so tiny, it's not legible, but the WiDS KE community will be sharing the interactive Python notebook where this is clear, and also for purposes of following through in detail on the steps we undertook, and also to enhance reproducible research. You know, the era we are living in is the era of reproducibility, and we encourage other people to also make use of what other teams are doing, get to learn, and even make improvements, add more knowledge and contributions to the field. Yeah, so at this juncture, I want to take us through what we gained from this, the key lessons that we took home as a team. Number one is we came to appreciate the fact that domain knowledge is very key in whatever machine learning task one is doing. After we got insights from the domain expertise through consultations and doing research, that's when our model performances began to make sense, and we realized very significant gains in terms of our leaderboard scores. The other key point to take home is that teamwork and collaboration is very key. So for this specific task, we worked in a team of 4, whereby we had to leverage on the various competencies and strength of the team members to collectively work on this project to ensure that it was a success. It was a very great experience because we got to learn from each of the team members. It was also fun in the process. And then lastly, but not least, is seize the opportunity. The 4 of us that worked on this project in this team can bear witness that we are really different in terms of a skill set in a positive way before this datathon. had we not participated in this datathon, we would really had missed a lot of learnings and knowledge and even experiences that have really added value and skill into ourselves as professionals, and even in terms of sharing ideas to mentor other people. Yeah, so just to encourage us, sometimes you might not see it as an opportunity. It might look very intimidating at first, but throw yourself in, and before you know it, you are learning something. So this was the key take home for us, and we hope you guys also resonate with them in one way or the other. And that's the end of my presentation. So I just like to request all of us to connect further on LinkedIn and collaborate on such kind of projects, share knowledge, and create impact to the society. So thank you very much for your time and attention. I want to hand it back to Millicent for the next session. Thank you.
Thank you very much, Brian, for a wonderful presentation. Yeah, and thank you for beginning by mentioning broadly about WiDS DATATHON. So everybody, like earlier this year, we took part in WiDS DATATHon challenge hosted by WiDS Worldwide community. And this wonderful presentation by Brian, just we were doing kind of like a recap of how we could have gone about doing, solving the challenge. And most of us did quite a great work, and just like Brian's team. So this is how they did it in their team, and I hope you learned a lot from what they did. And at this point, I don't know whether we have questions for Brian. In case of questions, please just feel free to paste them on the chat. You can ask questions about Brian's presentation, and also just general questions if you have. So the floor is open for questions. Yes, Samuel.
Yes, hi everyone. I think it is important to mention that we have a notebook on GitHub, which is much detailed, and